Hello and welcome to Equity Education, the chemistry version, and today we're going to be looking at empirical and molecular formula calculations, and then quickly we'll have a glance at percentage composition calculations. Okay, so I'd like you to open up your booklet and we'll start with some definitions. So, definition of empirical formula is the simplest whole number ratio of atoms of an element in a compound. And molecular formula is the actual number of atoms of an element in a compound. E.g., so if I had a molecular formula of C2H6, which, if you know, should be ethane, my empirical formula of my molecular formula, the simplest whole number ratio, should be CH3, because there's 2:6 ratio. I can simplify it to 1:3. Right, so moving on. Empirical formula calculations. So, empirical formula calculations can involve percentages. Therefore, to get a mass value, we can say that 100% is equal to 100 grams. And once we've defined this, then we should be able to do these calculations. Okay, so find the empirical formula of the compound containing carbon, hydrogen and bromine by mass in these amounts. It says by mass, it means by percentage abundance, or the percentage. Right, so the first thing we need to do is calculate the molar ratio of each substance by working out N. Well, we're going to use our formula N equals M over Mr. And I have carbon, what else do I have? Bromine and hydrogen. And I'm going to space them out. So I can say that my number of moles of carbon equals M divided by Mr. I know my percentages. I'm going to turn it into grams, so 22.02 divided by 12 gives me this. My N of Br is 73.39 over 79.9, my Mr, and my number of moles of H is equal to 4.59 over 1. Okay, so this gives me some values. This gives me a value of 1.84. I don't know why I've done it up here. 0.919 and 4.59. Okay, I can now divide by the smallest number of my moles here to get a whole number. Okay, so my smallest number of moles is my Br, so I'm going to divide by 0.919, 0.919, 0.919, and this gives me some values. So this equals about 2, this is obviously 1, and this is about 5. Remember, we're trying to work out whole number ratios. If you get 4.99, we can round it up to 5. If you get 1.5, you don't know whether to round it up or below, so you have to do something else, as you'll come on to in the next example. Right, so I'm going too far ahead. I've worked out that my empirical formula then is, I've got 2 carbons, I've got 5 hydrogens, C2H5, and I've got 1 bromine. So my empirical formula must be C2H5Br. So I worked out my number of moles using the percentages and convert into mass in the question, and then I divided by the smallest number of moles of whatever atom of the element it is to give me my whole numbers. Right, so pretty straightforward, I think. think you should be able to do the next question. So here we go. Calculate 1.67 grams of iron join with 1.44 grams of oxygen gas in an oxide of iron. What is the empirical formula of the oxide? Okay, remember you need to get a whole number ratio. Alright, so I'll give you a couple of minutes to do it, then we'll go through the answer. Okay, so let's go through it together. So I'm going to use my formula N equals M divided by MR. You may have noticed in this question we haven't got percentages, we've got actually masses, so I can just use my masses which are given. So 1.67 grams of iron, and the MR of iron is 55.8, which gives me 0.03 moles of iron. I now need to work out my number of moles of oxygen gas. Be careful, it's O2. So that means I have 1.44 divided by 32, 16 times 2, because I'm using O2, it's a diatomic molecule, which gives me a value of 0.045. Now I need to divide by my smallest number, which is over here, my moles of iron, 0.03, divide by 0.03, which gives me a value of 1, and over here I have a value of 1.5. Now these aren't whole numbers obviously, so I have to times both sides by a certain amount to get a whole number. I know if I times 2 here I'm going to get 3, and times 2 here I'm going to get 2. So we have to say that to get a whole number, times by 2 on both sides. When I mean sides, I mean the number of the Fe, the iron and the oxygen. So 1 times 2 equals 2. 1.5 times 2 equals 3. Therefore my simplest whole number ratio of this oxide of iron must be Fe2O3. Simple. Okay, so we'll carry on. So calculating molecular formula. So we'll do this by doing a question together. So determine the molecular formula given the following: compound containing 84.21% carbon, 15.79% hydrogen by mass, has a relative molecular mass of 114. Okay, find its molecular formula, calculate the molar ratio of each substance by working out N. So that's our first task. Calculate the molar ratio of each substance by working out N. Again, put in the corner, I'll be using N equals M divided by MR. And then I'm going to split it into carbon and only hydrogen, carbon and hydrogen. So my number of moles of carbon is equal to 84.21, because I've said that 100% is equal to 100 grams, divided by 12, which gives me a value of 7.02. My number of moles of hydrogen, 15.79, divided by 1, which obviously gives me 15.79. I now need to divide by my smallest number, as it says here, which is 7.02. So that gives me some values. What does it give me? It gives me 1 and 2.24. Okay, so 2.24. It's not a whole number, it's not even close to a whole number. So I need to convert this into a whole number. So I need to multiply both sides by 4. So 1 times 4 equals 4, and 2.24 times by 4 equals around 9. So that means my empirical formula must be C4H9. So I've only worked out my empirical formula so far. So, next part, calculate the molecular formula by dividing the actual MR by the empirical formula MR. Okay, so my actual MR is 114. My empirical formula, so, would be 12 times 4 plus 9, which gives me a value of 57. Okay, so this gives me a value of 2. So 2. And this number tells us how much we're going to have to times our empirical formula by. So the empirical formula by. Therefore, C4H9 times by 2 equals C8H18. My maths is correct. And then you can check your answer equals the MR of the molecular formula. So we would have 12 times 8 plus 18, which does equal 114. Therefore, I've worked out my molecular formula, which is the actual number of atoms of an element in a compound, as C8H18. Okay, so moving on, your turn. So we are going to do a calculation. So determine the molecular formula given the following. Analysis of a hydrocarbon showed that 4.2 grams of the hydrocarbon contained 0.6 grams of hydrogen and the relative molecular mass was 70. Find the molecular formula of the hydrocarbon. Okay, I'll give you about 5 minutes to have a go at this calculation. Okay, I'm sure you've all done it. Was there anything tricky in this? No, not really, I don't think. So, a slight first step is that we are only given the mass of hydrogen. So to work out my mass of carbon, I must have my total mass minus my mass of hydrogen, which is, what does it give us? It gives us 3.6. Now I can start doing my empirical formula calculation using N equals M over MR, carbon and hydrogen. So my number of moles of carbon is equal to 3.6, which is here, divided by 12, which gives me a value, I think, of 0.3. I will just check. Yes, it does. Okay, so equals 0.3 moles. Over here, 0.6 divided by 1 gives me a value of 0.6. I now need to divide by my smallest number, which is 0.3. Okay, which gives me a value of 1 and 2. So they both are whole numbers, so we can leave them as this. This is our simplest whole number ratio. So CH2. Okay, I now need to divide my actual MR by the empirical formula. So 70 divided by 12 plus 2 is 14. Gives me a value of 5. So this is the number that I need to times my empirical number by. So CH2 times by 5 equals C5H10, and then I can check to make sure my molecular formula is the same. So 12 times 5 plus 10, and let's just make sure, because I can actually do this calculation, times 5 plus 10. Don't know why I couldn't do that in my head. But anyway, it equals 70. So there you go. You have worked out the molecular formula of this molecule. Right, okay, so pretty straightforward as long as you follow the steps, and we'll quickly now move on to percentage composition calculations. We're just going to I will show you very, very briefly because they are quite easy as long as you use this formula. And so the formula for working out percentage composition is percentage composition of an atom is the AR of the atom that we're trying to calculate over the MR of compound times 100 e.g. So I'm going to have a look at doing this one. So what is the percentage composition of Si in SiCl4? I can use this formula. So my AR of the atom, so in this question it's silicon, is 28.1 over the MR of the compound, which is 170.1 times by 100 gives me a value of 16.5%. Okay, pretty easy. Okay, so this question is very, very similar, but we're not given a percentage. We're not asked to calculate the percentage. So what is the mass of sulfur in 500 grams of H2SO4? So here I would use the AR of the atom over the MR of compound. Because I'm not working out a percentage, I times by the total mass in question of the compound. So in this example, this equals my mass of the atom in question. So my AR of sulfur, that's what we're trying to work out, is 32.1 over the MR of H2SO4, which if you add them all up is 98.1, times by the total mass, which is 500, which gives me a value of 164 grams of sulfur. Okay, so very quick and straightforward, hopefully. And yeah, so the empirical and molecular formula calculations are easy, I think. You just need to give them a bit of a practice, and I hope that was useful as usual, and I will see you next time. Okay, bye bye.